Ever feel like current AI can see but not truly understand what it's looking at, especially, when the view changes?
Yeah, absolutely. Like how we just naturally piece together a scene from different angles.
Exactly, like navigating a crowded room or watching a sports game with cameras cutting all over the place. Getting AI, these multimodal large language models, MLLMs, to do that, it's been, well, surprisingly hard.
It really has. MLLMs have come so far. But integrating multiple visual perspectives, genuinely reasoning across them, that's where they still lag quite a bit behind us.
And it's a real bottleneck, isn't it? Especially for putting these models into complex, real-world situations.
Definitely. Which brings us to why we're doing this deep dive today. There's a really interesting new benchmark tackling this head-on.
Ah, the all-angles bench.
That's the one. It's specifically designed to test how well MLLMs can reason about scenes captured from, well, all angles, multiple viewpoints.
And we're going to be unpacking the paper that introduced it, the one focusing on relative distance, attribute ID, camera pose estimation. Basically, this is your quick guide to where things stand with multi-view reasoning in AI right now.
Our mission today really is for you, our listeners, the AI researchers, the ML engineers out there, to get a clear handle on the current limits of MLLMs in this multi-view space, and crucially, what this benchmark tells us about where research needs to go next.
Okay, so let's do a quick rundown up front, those key takeaways for you. First off, these MLLMs, they really struggle to connect the dots, identifying the same object from different camera views, figuring out how those views relate spatially.
Right. And interestingly, just telling them to think step by step using chain of thought prompts doesn't always help much with this multi-view stuff.
A big sticking point seems to be camera pose estimation. They just aren't good at figuring out where the cameras are relative to each other. And that messes up everything else, like judging direction or how objects are being manipulated.
But here's a twist. Some open source models are actually doing better than the big closed source ones on certain tasks, particularly those involving orientation. It suggests maybe specialized training really pays off.
Yeah, that's fascinating. And finally, consistency is a major issue. Ask a model basically the same thing, but from a slightly different viewpoint. You often get different answers. It shows a lack of, well, deep understanding.
Okay, so that's the snapshot. Let's dive into the details now.
Let's start at the benchmark itself, all angles bench. What was the core idea behind creating it?
Well, the motivation was really fundamental. The researchers saw that for MLLMs to truly understand and interact with the physical world, think robotics, augmented reality, they need a much stronger grasp of spatial reasoning, geometry, essentially.
And you can't really get that from just a single picture, can you?
Exactly. You need to integrate information from multiple viewpoints to build that coherent 3D understanding of how things are arranged.
So how did they actually build this benchmark? Sounds like a lot of work.
Oh, it was definitely systematic.
Yeah.
They manually picked out 90 different multi-view scenes. Most of them, 83, came from the XO4D Data Set.
That's the one with first-person or third-person views, right?
Yeah, egocentric and exocentric views, really rich data. And then 7 more scenes came from EgoHumans. The key thing is, every scene had at least 3 different camera viewpoints. And they standardized the images too. 796 by 448 pixels.
And they made sure the scenes were varied, not just like office environments.
Absolutely. They covered indoor, residential, even industrial settings, lots of different activities. The goal was to avoid biasing the benchmark towards one specific type of environment.
Smart. So after collecting the scenes, they designed the actual tests, the tasks.
Right. 6 main task categories, each designed to probe a different aspect of multi-view reasoning.
Okay, break those down for us. What were they testing?
Sure. First, counting. Simple enough. But can the model count objects accurately when maybe you can only see some from one view and others from another?
Ah, requiring integration. Makes sense.
Second, attribute identification. Recognizing the same object and its features, like color or shape, even when viewed from different angles.
Testing object constancy. Got it.
Third, relative distance. Understanding how far objects are from each other or from the camera, considering the different perspectives.
Okay, spatial relationships.
Fourth, relative direction. Similar, but about direction is object A to the left or right of object B, considering the viewpoint.
Tricky, because left and right change with perspective.
Exactly. Fifth, object manipulation. This looks at whether the model understands changes to an object, its position, its state as seen across the different views.
So tracking changes across perspectives.
And finally, number 6, and this is a big one, camera pose estimation. Can the model figure out the spatial layout of the cameras themselves? their positions, their orientations relative to the scene and each other.
That feels absolutely crucial. Like you said earlier, if it doesn't know where the eyes are.
Its whole spatial understanding is compromised.
Yeah.
It's foundational. But they added another really clever layer on top of these tasks.
The paired questions.
Yes, this is where they really tested the depth of understanding. They didn't just ask one question per scenario.
What did they do?
They systematically created pairs of questions. They'd rephrase a question, maybe swap the viewpoints mentioned, or change the orientation focus, like asking about left in view A versus right in view B. But the underlying visual reality, the ground truth, stayed the same.
Ah, so you gave that example earlier. Is the cup left of the book in view A paired with is the cup right of the book in view B if the views show the same scene from different spots?
Precisely. It tests if the model has a consistent understanding or if it's just guessing based on superficial cues in one specific image or phrasing.
That's a really smart way to check for robustness. Did they do this for most questions?
Yeah, a huge chunk, 85.3% of the questions, excluding the counting ones, had these paired counterparts.
And they needed reliable answers for all these questions, right? So human annotation was involved.
Definitely. Very rigorously done. 8 PhD students, all with NLP or computer vision backgrounds, manually annotated everything. They had detailed guidelines, a multi-stage verification process, even a special GUI platform to make sure the annotations and ground truth were accurate.
So a solid benchmark. Okay, let's get to the main event. How did the MLLMs actually do on All Angles Bench? Which models did they put through their paces?
They tested a really good spread. On the closed source side, the big names, Gemini 2.0, Claude 3.7, GPT-4O.
The usual suspects.
Right. And for open source, a lot of recent powerful ones. DeepSeek VL2, Quina 2.5 VL, Intern VL 2.5 Cambrian, plus different versions of Lava and OVS.
A comprehensive list. And they made sure the testing was fair?
Yes. They set the temperature to 0 for inference. That means the models give deterministic outputs. The same input always gets the same output. It removes randomness and focuses on the model's core ability.
Okay, and did they compare this against humans to get a baseline?
They did. They took a random subset of 250 questions and had different PhD students answer them independently. That gave them a human performance level to compare against.
And the big reveal, how did the AI stack up?
Well, the headline result, looking at Table 1 in the paper, is a pretty significant gap. Across the board, both closed and open source MLLMs perform substantially worse than humans on these multi-view tasks.
Not too surprising, maybe, given what we discussed, but still significant. Where were the biggest weaknesses?
One major finding, maybe the most critical, is that MLLMs really struggle with viewpoint reconciliation, basically putting the different views together coherently.
And that showed up most clearly where?
In the camera pose estimation task, humans got around 88.9% accuracy in ordering the camera perspectives correctly, the best MLLMs. They were lagging by over 50 percentage points.
50 points, that's huge.
It is. Some models were barely better than just randomly guessing the camera order.
Wow, what kind of mistakes were they making? How did they fail to estimate the poses?
It often came down to failing to understand how the scene transforms between views, like not getting how things should look different if the camera moves left or rotates. They also just missed the underlying 3D geometry. Figure 9 in the paper shows this, well, models trying to map out camera positions and just getting it completely wrong, even with text reasoning.
So they're stuck in 2D, essentially, not building that 3D mental model from the different 2D inputs.
That seems to be a core part of the problem. And as you'd expect, if you can't figure out the camera setup, it really hurts performance on other spatial tasks.
There was a counterpoint, right? Something about open source models.
Yes, this was finding number 2 and quite fascinating. Certain open source MLLMs actually excelled in orientation-sensitive tasks. Specifically, OVS 234B and Qwen 2.5 VL outperformed even top closed source models like GPT-4O on object manipulation and relative direction.
Really? That is interesting. Why might that be? Do the researchers have a hypothesis?
They suggest it might be down to the architecture and training of those specific models. OVS and Qwen seem to have robust video understanding capabilities and fine-grained visual grounding modules. The Qwen team's own report mentions focusing on these aspects.
So training on video, even though these are static image tasks, might help, because video inherently deals with changing perspectives and orientations over time.
That's the thinking. The training emphasizes frame-by-frame orientation tracking, spatial grounding, skills that seem to transfer surprisingly well to reasoning about multiple static views.
Whether the closed source models use similar video-heavy training isn't always clear, I guess.
Exactly. but it strongly hints that domain-specific training and architectural choices really matter for these geometric multi-view challenges. It's not just about scale.
That's a key insight for anyone building these models. Okay, let's talk about consistency. You mentioned the paired questions were designed to test this. What did that analysis show?
Right, the Inconsistency Analysis. They looked at pairs of questions that were semantically the same but phrased differently or from different viewpoints. They categorized the results, both correct, CC, both wrong, WW, or inconsistent, IC, where the model got one right and one wrong.
And those IC cases are the revealing ones, suggesting a shaky understanding.
Precisely. Figure 5 of the paper lays this out. One really striking point. GPT-4O showed incredibly high inconsistency, around 70%, specifically on relative distance tasks.
70%. That's huge. Any idea why GPT-4O struggled so much there compared to others?
The paper doesn't pinpoint the exact reason for that specific model and task, but it highlights a broader trend. All models found relative direction very hard, with inconsistency rates over 40% across the board. Understanding orientation changes is just tough.
So even if a model gets one question right, it might fail the paired one, showing it didn't truly grasp the spatial layout.
Exactly. It might be relying on superficial cues, not genuine geometric reasoning. The high inconsistency rates really point to the brittleness of current models' multi-view understanding.
Did they look at whether better prompting, like chain of thought, could help bridge this gap, especially when information is split across views?
Yes, they experimented with different CAT strategies, specifically for the counting task. They compared scenarios where all objects were visible in one view versus needing multiple views to see everything.
And did thinking step by step help the models integrate information across views?
The results were mixed, actually. Figure 7 shows it. For some models, like GPT-4O, using certain code T-Proms like zero-shot code T or identification code, did give a boost in those partial visibility counting scenarios.
But not always.
Right. For models that were already pretty decent at multi-view counting, like Intern VL2.538b, adding these code T-Proms sometimes didn't help much, or even made performance slightly worse.
Interesting. So prompting isn't a magic bullet here.
It seems not. The suggestion is that fundamental improvements likely need more than just clever prompting. You probably need architectural changes, maybe specific modules for spatial reasoning, and better, more targeted training data. Figure 6 even shows GPT-4O sometimes just defaults to counting within each view separately, instead of properly merging the counts when faced with partial visibility.
It reinforces that idea of needing deeper, built-in spatial capabilities. And they used visualizations too, didn't they, to see why models failed on camera poses?
They did. Inspired by some previous work, they prompted GPT-4O and Gemini 2.0 Flash to basically draw or describe the infer layout, object positions, camera positions, orientations.
Like asking the AI to sketch the scene setup.
Sort of, yeah. And the results, shown in figures 8 and 9, were quite telling. The visualizations confirm that errors often stem from that failure to reconcile viewpoint transformations. Models would create misaligned camera coordinates, ignore background cues useful for geometry.
Even when they tried to reason about it.
Yes. Even when the models generated text explaining their reasoning for, say, the camera order, like in figure 9, the final ordering was still completely wrong. The reasoning didn't connect properly with the visual geometry.
It all comes back to that fundamental disconnect in understanding the spatial relationships between views.
It really seems to be the core issue. And just to highlight how tricky some of these tasks are, the paper even includes examples where the human evaluators got questions wrong.
Oh, really? Even humans tripped up sometimes.
Yeah. Figure 22 shows some examples, things like perspective illusions, objects being hidden, occlusion, or just missing small details when comparing multiple complex images led to human errors in tasks like relative distance, direction, and even counting sometimes. It underscores that this benchmark sets a genuinely high bar.
So, wrapping this up then, this deep dive into the all-angles bench shows pretty clearly that MLLMs, even the best ones, have quite a way to go to match human multi-view understanding.
Definitely. Viewpoint reconciliation, camera pose estimation, consistency across views, these are major hurdles remaining.
But it's not all bad news. There are promising directions, right?
Absolutely. The performance of models like OVS and Quinn hints strongly that specialized training, maybe focusing on video data and architectural tweaks like adding spatial modules, could be key. It suggests a path forward.
And the benchmark itself, all-angles bench, seems like a really valuable tool for the community now to measure progress and focus research efforts.
For sure. Getting this multi-view perception right is so fundamental for the next generation AI, especially anything interacting with the 3D world or even 4D dynamic scenes.
So the final thought for you, our listeners. Given these limitations we've discussed, how might this affect the AI systems you're working on? If your system needs to understand scenes from multiple angles, what are the implications?
And perhaps more importantly, what innovative ideas do you have? What kind of architectural changes or training strategies could help bridge this gap between current AI and robust, human-like multi-view perception? That's the challenge ahead.